So here's my lab setup. You can see this brass ball with a thermocouple attached to it, and there's a thermocouple amplifier, and it's just powered by 3.3 volt, and then it uses SPI protocol to communicate with the Nucleo. And that's basically the setup. It's pretty simple. And then, of course, use STM32. And then I can show you how I collect data. So there's a UI task in the code that allows me to trigger data collection with this blue button, and then it'll turn on a little green LED. There we go. And now it's collecting temperature data along with time. So you can see it's a little bit hot in my room right now because it's a hot summer day. Yeah. And then as far as calculating the convective heat transfer coefficient, which is happening between the brass and water. Here are the governing equations. So we're using lumped thermal capacitance. And then when we actually collect the data, we can generate a plot that allows us to calculate this time constant, because as you can see, it's in the exponent of the best fit equation. And then we kind of work backwards, and we have all these parameters and values that we can find in the book or in the lab handout. And then eventually we get here to H. And then they're basically all like known parameters, plus that time constant that we got from the data collection. And then we get, or I got 232 watts per meter squared Kelvin. And yeah, that's about it. And oh, the lumped thermal capacitance, in my situation at least, is a fair approximation because the Biot number is below 1 by a lot, as you can see.